All right, everyone, welcome to our third meeting. Today we're going to be talking about just an intro to forecasting thunderstorms in general. Next meeting, we're then going to talk about wind shear and how those affect thunderstorms. But to get started today with forecasting storms, we're going to need to learn a little bit about these things called SkewT log P diagrams. These are very important for understanding how thunderstorms work from a conceptual standpoint. So just to start, the vertical axis of these diagrams represents height or pressure. Usually they're graphed at standard pressure levels, each of these constant lines here. And the pressure lines are arranged logarithmically because pressure decreases exponentially in our atmosphere. And that's so that the height ends up being about linear when you go up. That's where the log P comes in the name logarithmically arranged pressure. We're going to talk about where the SkewT comes from now, and that's from the quote unquote horizontal axis, but it's actually skewed a little bit. These are lines of constant temperature, and they're skewed that way so that you can fit a large range of temperatures in a fairly compact diagram. Otherwise, all your diagrams would be like widescreen. So this just makes it a little more convenient to fit things into more of a square shape. Next up, so the two main things that get plotted on these diagrams, you have your lines, your line of temperature with height, that's in the red here, and your line of dew point temperature with height. And all that dew point is, in case you're unfamiliar with it, it's the temperature that you need to cool air down to at a constant pressure in order to saturate it. More technically, it means that the rate of evaporation equals condensation. That's when you start to form clouds. So there are a couple more technical things we need to talk about. These are called lines of constant potential temperature. And all it is, it's just the path that a parcel of air will take if you move it up or down in the atmosphere without heating it in any way. That could be from the sun, it could be from energy released from condensation or lost from evaporation. As long as none of those things are happening and the air is just moving up or down, its temperature will follow these lines. So they're very important for a lot of processes in the atmosphere, as we'll see later. And finally, we're going to talk about lines of constant mixing ratio. You can think of mixing ratio as like the water vapor content of the air. And these lines just show you how the dew point of a parcel of air changes if you keep its mixing ratio constant. So that's what these lines represent here. Now we're going to move on to the LCL and cloud-bearing parcels. So let's say we've got a parcel with the surface temperature in this particular sounding and the dew point. And let's say we just give it a nudge upwards, say a front comes along and lifts it up, or air is blowing up a mountain, something like that, just to get the air moving upward. This is how its temperature and dew point will change as it does so. You can see that what happened is as we lifted it up, the temperature followed that line of constant potential temperature, like I was talking about earlier, and the dew point followed that line of constant mixing ratio. And you can see that as that happens, eventually the two come together and actually meet. So you get condensation and a cloud begins to form. That's really important because once clouds begin to form, energy gets released, latent heat. And that means that as the air continues to rise, it'll cool at a slower rate than it otherwise would. And the height that the condensation occurs at is called the lifted condensation level, although you'll almost always hear it just referred to as the LCL because it's just easier to say. But because of that latent heat release from condensation, this white line is the path that the parcel will now follow from here on out as long as condensation continues to happen and it continues to rise upward. So now, with all this in mind, we're ready to talk about buoyancy, which is the main driver behind updrafts, which is what thunderstorms form from. So if a parcel is cooler, in other words, more dense than its surroundings, it experiences a downward acceleration. On the contrary, if it's warmer, it will experience an upward acceleration. So we have this positive area representing CAPE. It's an abbreviation for convective available potential energy. And then negative area, which we call SIN, it's an abbreviation for convective inhibition. All these are is just a measure of how much energy is available to convert to kinetic energy as a parcel is accelerated through it. On a more technical note, if you've never heard of virtual temperature, don't worry about what I'm about to say. But I should be using the virtual temperature here to calculate these buoyancies. I'm just using the regular temperature because the virtual temperature in the environment isn't plotted in these soundings, and it's a little tricky to determine it otherwise. So just for the purposes of these conceptual diagrams, going to be using regular temperature. So now let's try and lift an air parcel to this positive area, because if we get it to there, theoretically, it'll start accelerating upwards and we've got ourselves a thunderstorm. Easy peasy, right? So let's just send it upwards. All right, it's starting to go up and uh-oh, that's not good. All right, so it came right back down. Here's the problem. It can't make it to the positive area because it has to go through this area of negative buoyancy that's accelerating it downward. So it just tries to go through and then it comes right back down. So as you can imagine, we want to get rid of this area of sin if you want to make a thunderstorm. So it has to be significantly weakened or removed entirely. So now we're going to talk about how we might go about doing something like that. So what you can do to get rid of sin is lift air upward. So we have a sounding here. We have convective inhibition that's preventing convection and storms from firing. And now we're going to track these three parcels of air in this layer of warm air that's causing the sin. And we're just going to give these three parcels of air a nudge upward. Let's say it's being lifted upward by some unknown mechanism. And as it gets lifted upwards, you can see that it cools down according to the potential temperature lines that I was talking about earlier. And an interesting thing begins to happen over the course of 2 hours as it lifts up. You can see it cools enough that the sin actually goes away. And another consequence, if you were following that magenta circle, you can see that the moisture actually got lifted up as well. And both these processes, the cooling of the air in the layer of sin and the vertical transport of moisture, both make convective initiation easier. So you may be wondering, well, what's this lift you're talking about? You've been being very vague about it. And now we're going to talk about what this lift is and where it comes from. So there are two ways to get lift in our atmosphere. And they both have to do with the conservation of mass. So you can either remove mass from the top of the atmosphere. That way, in order to conserve mass, air has to move up towards it, or you can have lower level convergence. Now, these two types of lift play different roles when it comes to convection. Your upper level divergence is usually more of a primer for convection. It's almost never strong enough to actually directly initiate storms, but it can weaken that convective inhibition that we were talking about earlier. So it's still very important to identify. Your lower level convergence, that'll come in the form of fronts usually, or some other form of lift like air flowing up a mountain. That's what actually directly triggers convection usually. So it's important to know the difference between those two types of lift. They're both important, but they play different roles in priming the environment for storms. So now we're going to talk about some of that upper level divergence and where it comes from. Let's say we've got a gradient in heights here. Let's say this is in the mid levels of the atmosphere, like 500 millibars, say. Wind above the boundary layer doesn't experience a lot of friction because it's so far away from the ground. In fact, the two main forces that act on air at this height are the Coriolis force and the pressure gradient force, or the height gradient force, depending on how you look at it. This is called geostrophic balance. You'll learn about that in detail in classes like synoptic and dynamics. But the upshot is that wind usually flows parallel to height or pressure lines in the mid to upper levels of the atmosphere. So now let's perturb these height lines a little bit. Let's say there's a little kink in them. You have a little bit of a trough. So lower heights extend further down than their surroundings, and you get a trough. What happens then is the wind, it has to flow parallel to the height lines. So as it swings around the base of this trough, you can imagine it gains some intrinsic spin in here, right? So you can kind of see as it comes around, you can kind of see that spin in there. We call that vorticity. It's a very important quantity. You'll learn about that in detail as well as you move through this major. So now looking at the pattern of vorticity, you can see it's maximized along the base of the trough where the wind turns the most. We call it the axis of the trough. So all this is well and good, but how do we get divergence out of this? So let's say we have a parcel of air, some blob of air entering the shortwave. As it enters the trough, its spin is going to speed up because it has to. And then as it swings around the trough and exits it, its spin has to decrease. And as its spin decreases, it spreads out. You can think about if you've ever spun yourself around in an office chair. As you extend your arms outward, you slow down. And as you pull your arms in, you speed up. So, you can think about starting with your arms pulled in, and then you spread your arms out and you slow down. It's the same thing happening here. As the parcel spin decreases as it exits the trough here, just give it a sec. Yeah, so as it exits the trough, it's forced to spread out from conservation of angular momentum. And that spreading out is the upper level divergence that I was talking about earlier. So just looking at a real world example, you can see we have a trough here. They're typically a little more subtle than the example that I showed earlier. So it's good to see one in real life. So doing the same thing here, the vorticity decreases as it travels to the east. You get that spreading out motion. So you would expect this area here to have the highest vertical velocities. And if we look at the vertical velocities lower down, that is indeed the case. So this stuff actually works. That's good to know. And now we're going to send you guys into breakout rooms, and we're going to talk about how many short waves you can identify in this image here. And then we're going to come back together and talk about it. So, all right, looks like we have everyone back. So just to start out, does anyone want to volunteer to pick out one of the short waves that they found? Just say like what general location it's in.
The Dakotas.
The Dakotas. Yep, that's one. Does anyone have any other ones? Any other ideas?
Yeah, I said like Oregon/Washington.
Yeah, that's the big one. That's the big boy. Yeah. Does anyone have any of the more subtle ones, maybe in the southern or eastern part of the country?
Western Texas.
Yeah.
Kind of.
Yeah, that's one of the more subtle ones.
The one over Andy's house.
The one over Andy's house.
I really wanted to take that one for myself, but I was gonna be generous and let someone else do it for me, you know.
Any others? Think there's one or two that we didn't get.
I don't know where Andy lives.
He lives in Memphis, Tennessee.
Okay, so that one's gone. All right, and we said Texas, we said the Dakotas, and we said the Pacific Northwest.
You got it, buddy.
How about off the Panhandle of Florida?
Yep, that's the other main one. So let's just pop all those up there. So all these blue lines are the short waves. We got the big one up in Pacific Northwest, the one in the Dakotas. You've got one over northern Mexico, Texas Panhandle, Andy's house, and Gulf of Mexico.
Is there any length that has to be in order to be? Is there like any length that the wave has to be before it's no longer considered a short wave?
I don't know. It's kind of one of those vague things. A short wave is generally the wavelength is on a smaller length scale than your bigger troughs and ridges.
Right. And are they basically just identifiable by having a strong vorticity advection?
Yeah.
Or not necessarily strong.
Yeah, it's a trough in lower heights, and then there's a vorticity maximum along that trough axis. Those are really the two requirements. And it needs to be, it can't be like a huge trough. It's got to be on a length scale of like a couple 100 kilometers or so.
Okay. One thing that might one hint that might be like a really obvious giveaway that you're dealing with a long wave, not a short wave, is if you can identify like individual short waves or, little along a really big trough. So if it's big enough that it has its own little waves riding along it, it's probably a long wave.
Yeah,
just for reference.
long wave troughs will have short waves embedded within them.
So yeah, I was kind of hesitant about the one in Oregon and Washington just because it's a pretty
Yeah, that's kind of borderline. I mean, this time of year, I was looking earlier today for maps of short waves, and I mean, this time of year everything's really amped up because we're heading into winter. But normally in the spring or summer, they tend to be a little weaker and tougher to spot. So more like the ones over the central U.S. and Gulf. You probably won't see a trough like this in June or whatever, but maybe in May you would see something like that. So that was very good. In these, you can see most, in pretty much all of these troughs, you have positive vorticity advection is what we call it. So you have that decreasing vorticity here, here, here. That's where you would expect that lift where you could potentially weaken sin. So now we're going to move on to mesoscale lift. What we were talking about before was synoptic lift on the large scale, mesoscale on a smaller scale. These are what can actually trigger thunderstorms once you mix out the convective inhibition. So there are three main things that can trigger storms. The first one is going to be surface heating. So energy from the sun heats up the ground, which in turn heats up rising parcels of air called thermals. Those thermals become buoyant as they're surrounded by cooler air and they rise upward. And those, if they become strong enough and you have a weak enough cap, those can be enough to initiate storms. So you can imagine the sun begins to heat up these thermals and they rise upwards. That's probably the simplest one, the most obvious one to a lot of people. Second one, fronts. And I'm being pretty broad with my definition of fronts. I'm going to include warm, cold, dry lines, which are fronts between, which are boundaries between dry and moist air, as opposed to a temperature front. Outflow boundaries, which is a boundary between rain-cooled air from an older storm and some other air mass, or even sea breezes. I'm being pretty broad with that definition, but it's pretty much anywhere, any kind of boundary between two different air masses where air comes together and is forced upwards. So you can imagine, in this case, air gets forced upward by the front, and that's another pretty obvious way that you can get lift. The third is orographic. You have wind flowing up the slope of a mountain, or not even a mountain, just terrain that increases in elevation over a distance, and you have winds that are strong enough, you can get some upslope flow is what it's referred to, and that can be enough to initiate convection as well. So now we're going to put it all together. If you may have noticed that this sounding on the right is actually the result of the mixing out of the sin from the earlier animation. So it now has no sin, and we're going to see what happens. So let's say one of those trigger mechanisms come along. Let's say it's like a cold front or something, and it gets lifted up. Now, when it reaches its LCL, it's off to the races. There's no sin to prevent it from rising. It'll accelerate upwards, and then eventually it gets slowed down as it becomes negatively buoyant above this level here, which we call the equilibrium level. So with the sin gone from large scale lift earlier in the day, the air is free to accelerate throughout the layer with lots of positive buoyancy, and a thunderstorm is born. So that's really the basics behind what it takes to make a storm. If anyone has any questions, if anyone has any questions, please ask, because we're going to jump now into a little bit of a forecasting exercise to apply everything. So if there's anything you don't understand or want me to clarify or elaborate on, please ask away.
What was the potential temperature meaning again?
Yeah, let me go back to that. All right, so do you remember the whole way back to the first meeting when I was talking about what happens when you lift air upwards and its pressure changes?
Yeah.
Okay. This is basically the same process. That's what potential temperature is. It's basically conservation of energy. So it's how the temperature of something will change if it's if you have conservation of energy and it's not being heated or cooled in any way. So the only thing that's changing its temperature is the compression or expansion by the changing pressure around it. That's what these lines of potential temperature mean. Does that help clarify it?
Yeah, it does. Thank you.
So what you're going to be tasked with doing when I send you guys to the breakout rooms, you're going to have 2 time steps here. So this is 18Z mid-afternoon, 21Z late afternoon. You have 4 of the same parameters being mapped at those 2 different times. And you're going to try and determine, based on everything we've talked about, you know, the short waves, the lifting mechanisms, the instability, where the most likely place for thunderstorms to initiate is. So this is a little bit more open-ended. I encourage you guys to discuss it with your breakout room members to try and put everything together. The 4 things that you'll be looking at, we have 500 millibar vorticity. We have 2 meter dew point. Just a hint, this is going to help you identify a certain kind of boundary that's going to be important to the forecast, these dew points here. We have CAPE, and then we also have convective inhibitions. Those are the 4 things you're going to be looking at, 18Z and 21Z. So I'm going to send you guys to breakout rooms, try to figure out the screen sharing thing, and you guys will have ample time to discuss it because this is, like I said, pretty open-ended. So we're gonna go over what you guys were looking at. Does anyone want to volunteer their thoughts, what their room was talking about?
I will. Just brief, I'll get things started and then I want to see what other people have to say. But I think the big focus we talked about in our room, like the big theme was like, if you look at this setup, you know, it's a marginal setup and you have to really focus on where's the kind of like that Goldilocks zone where, you know, CAPE is maximized, but SIN is minimized. And it's very small in both time and space. And that's what we were looking for, like most importantly. Obviously, you use the upper air charts and the surface charts to orient you with respect to the shortwave and make sure like it makes sense where you're looking to begin with. You see a little shortwave, you know, in east central New Mexico. You look a little upstream or downstream from that, you know, you see that's where you end up finding your Goldilocks zone after you study the other 3 maps carefully and look for like, yeah, is anything, that's all I wanted to say is kind of, it's not an obvious like big bullseye or anything. It's very small, narrow window and corridor where you're looking to see storms in a setup like this.
Yeah, that is definitely the case. Any other thoughts? Does anyone want to comment on what they found looking at the SIN charts in particular?
I noticed that the SIN decreases a little bit from the 18Z to 21Z image, which I guess means is less of a lid, so the storms will be able to develop easier as time progresses.
Is there anything you noticed about like where the SIN is decreasing the most?
I think it was like the Oklahoma-Texas Panhandle, if I remember correctly.
Does anyone have any idea why that might be in relation to maybe one of the other maps?
Oh, I'm gonna do it. So yeah, if you look, you know, yeah, there's the SIN decrease in general across most of the region, but you look where it's decreasing the most and where it's like that's most notable. In other words, like where is it going from a smaller amount to an even smaller amount where it's even more meaningful? It's right along the boundary, you know, the front, you'd say one of those fronts that Sam was talking about earlier, you know, and you look, you know, yeah, you know, in the highest CAPE bullseye, you know, across sides, you know, where would that be, you know, just south of the Texas Panhandle across like, you know, you see it on the map, I'm sure, like where the most plentiful CAPE, you know, in the middle of that second image, right? But like, storms aren't going to form in the middle of that yellow area. They're going to form closer to that gradient because the SIN is eroding faster there due to a lot, you know, focus of moisture convergence, you know, and temperature convergence, and, you know, a variety of things I'm sure Sam would want to talk about that are like helping to enhance things, what goes on near the boundary, because you need some mechanism to erode that SIN, because oftentimes it's too much just for like a sunny air up day thermal to just kind of punch through.
Yeah. So you can see across across this entire dry line boundary, the SIN decreases, but you see in this area in particular, it decreases even more. And if you notice, that's right where the shortwave is. So you have, air coming out of the shortwave. Your divergence is generally in this area, and well, would you look at that? That's where the SIN decreases the most. So yeah, so it's important. There are a lot of things that you can look at to determine that. So that's very good. All really good points that you guys were talking about. And I think all the thoughts that we had generally led us to this area here. You can see you have the lift from the shortwave. You have the low-level convergence along the dry line. There's ample instability, and the SIN has decreased the most there. So that's kind of the area that I think a lot of you guys focused in on. And that's good, because if we take a look at the soundings in that area, this is at 18Z. You can see you have that cap there, that stout cap. And then as we move into the next time step, you can see the moisture gets vertically mixed, and you mix out that cap a little bit to the point where it's marginal. It's not a slam dunk by any means, but if you have strong enough lift along that dry line, you could very easily get storms to pop here. So taking a look at what we were looking at before, does anyone notice anything about the timestamps on these images? Anything that sticks out?
They're right now.
Yeah, pretty much
Yep.
now.
They're right now. If you look at radar right now in this purple, generally in this magenta area, you'll see storms popping off. They're not crazy or anything, but it is definitely happening. And looking at the SPC outlook here, you can see the initiation zone is right on the northwest edge of this marginal risk that the SPC outlined. So what you guys just did, it's what the SPC does, the best severe weather forecasters on the planet. So all this stuff put together, you were able to determine where storms were going to fire. I think that's pretty cool, honestly.
Sam, you mind if I say something? Because I want to make sure my group wasn't confused based on something you said.
Yeah.
So like I know, I did mention to some people in my group that obviously it's about 0Z right now, which is 3 hours, to be, nitty picky, it's 3 hours after this. So like,
yeah, so it'll be a little further.
If you see the storms a little further east than where you precisely where you expected, that's not necessarily mean you're wrong. It just means it's progressing eastward as the system normally would with time.
Yeah, that's a good point. Yeah. So that wraps up my presentation. If anyone has any last questions on anything that I talked about today, feel free to ask.
All right, I'll ask the question. All right, so yeah, so we were talking, I love this marginal case up because it makes you think. So like one thing I was thinking about, and I want to hear your thoughts on it too, was like, obviously we expect these storms to form close to the dry line, not necessarily like in the Cape Bullseye or in the moistest airness, right?
Yeah.
So like you discussed and explained, but if someone were to look at the radar right now and they see like, oh wow, these storms are pretty much at the same latitude as the Texas-Oklahoma border, right, along the panhandle. So like they're a little further east right now. And you might like look, if you looked at meso analysis right now, if you're really nerdy and wondering or like curious, you notice that they kind of moved off that boundary a little bit. But that's not uncommon, like oftentimes once you get a storm to form, right, Sam, it's easier for it to maintain itself in a slightly less favorable environment if it's already going.
You're starting to get into what we're going to talk about next meeting, which is all about wind shear. Yeah, you're going to spoil it.
Right.
So
yeah, that's all I'm going to say about that then.
The point, I think the main point of today's presentation was to talk about how you forecast storms in general. But with the next meeting, we're going to talk about wind shear and what happens once storms form. So, what the wind shear does to those storms. So, this whole presentation, you can think of it as will storms form? And then the next presentation will be if storms do form, what will they do? So that's kind of the general organizational structure that the next meeting is going to take. that was dead on. You almost just spoiled my entire next presentation. So thanks for that, I guess.
Lips are zip now, Chief.
All right. Well, thank you for listening to me ramble on for a while about this stuff. Yeah, if you guys have any questions after the meeting, you can always, ask something in the group chat. I would love to hear your questions or whatever. This is a lot of fun to do. Yeah,